let's discuss concavity. A function f in my interval is differentiable. But we say that the graph is concave up if f prime is increasing on the entire interval. Now please note what that means. When you're back here, the slope is negative. As a matter of fact, it's quite steep negative, and it becomes less negative. That is considered f prime increasing, okay, until it comes up and it becomes positive. You can think of something being concave upward if you can make a smile out of it. It's happy to be concave up. Now a function is concave down if f prime is decreasing on the interval. So here f prime is positive, but it is decreasingly positive, and here it is becoming more negative. So we can see here a function is concave down if it curves downward. A lot of times we talk about smiley faces and frowny faces. Now, the test for concavity is quite straightforward. If the second derivative is positive for all x in an interval, then the function is concave up in that interval. While if the second derivative is negative, then the graph is concave down. To do these problems, you know where we're going. I'm going to want you to take the second derivative, so take the first derivative, take the second derivative, find where the second derivative is 0, set up your intervals, and then test to see if f double prime is positive or if f double prime is negative. So let's start with this one. Let's sketch and determine the open intervals where f double prime is positive, or it's concave up or concave down. All right, so the function is f is 6 divided by x squared plus 3. Now, I'm going to rewrite this as 6 times x squared plus 3 to the negative 1. You could use the quotient rule, but I don't want to. So f prime, I don't want to yet. So f prime is negative 6 times x squared plus 3 times 2x. And I'm going to rewrite this as negative 12x divided by x squared plus 3 squared. Now I need the second derivative. Let me change pen colors. The second derivative is equal to, now you can set it up. I don't really have enough room to set it up, so I'm going to take the derivative of this. I'm just going to tell you that the second derivative is 36 x squared minus 1 divided by x squared plus 3 cubed. All right, now you can find the second derivative easily. Now, where is this 0? The first thing you have to do is find where f double prime is 0. F double prime is 0 when the numerator is 0. So when x is plus or minus 1. The denominator in this case is never 0. So we're going to need to test the intervals from negative infinity to negative 1, from negative 1 to 1, and then from 1 to infinity. Now, again, just like we did with the first derivative test, you can pick any value you want. I am going to pick x equal negative 1,000. That's my favorite one. When possible, I pick x equals 0. And then here I'm going to pick x equal 1,000. Now, what's the sign of f prime? We're going to come up here and we're going to do the sign thing again like I did before. When x is 1,000, negative 1,000, then my denominator is, well, negative 1,000 squared is positive, so my denominator is going to be positive, and my numerator is going to be positive, and my denominator is going to be positive. So this is positive, and this should be f double prime, not f prime. And the conclusion is it is concave up. Okay, and I put a little smile there. Between, or excuse me, at x equals 0, let me switch colors here. At x equals 0, this is, the numerator is negative, the denominator is positive, so the second derivative is negative, so this one is concave down. A little frowny face. Now when x is 1,000, and again you can pick anything you really want, what do I have? The numerator is positive, the denominator is positive, so the sign of the second derivative is positive, so again we are concave up.